Hello students, this is Dr. Sanjay Kumar Sahu. As discussed in our introductory lecture, we will cover the entire syllabus through video lectures, and the entire syllabus we divided into 4 modules. And today we are going to discuss the first video lecture for module number 1. The module number 1 was consisting of these topics, and from these topics we are going to discuss first 2 topics, namely band theory of solids. We will discuss band theory of solids, and we will try to classify the solids into conductors, insulators and semiconductors. Now, before going to classification, let us discuss what is band theory of solids. Band theory of solids is nothing but the study how the energy levels of the valence electrons of an atom get modified when atoms comes close together to form a crystal. In other way, band theory of solids tells us how during the process of crystallizations the energy levels of valence electrons get modified. To have a physical picturization of this, let us consider an atom of any arbitrary atomic number. Let us consider the atomic number to be 14, and the electronic configuration for this atom will be 1s2, 2s2, 2p6, 3s2, 3p2. In this electronic configuration, for this atom, there will be 3 cells, n equals to 3. That means there will be a k cell, there will be a l cell and there will be a m cell. And k cell is consisting of one subcell, that is called S. L cell is consisting of 2 subcells, one is called S, one is called P, and M is also consisting of 2 subcells, one is called S, one is called P. The first cell is completely filled with 2 electrons. There is no vacancy, it is completely filled. The second cell is also completely filled with 8 electrons. 2 electrons are there in S subcell and 6 electrons are there in P subcell. So, in a total there are 8 electrons in the L cell. In the M cell, though there is a chance of 8 electrons to stay there, but there are only 4 electrons. It is not completely filled. Out of these 4 electrons, 2 electrons are there in the S subcell and 2 electrons are there in P subcell. So, out of 6 vacancies of the P subcell, only 2 vacancies are filled with the electron and rest 4 orbitals are unfilled. Vacancies or orbitals are unfilled. If you want to draw a energy diagram, energy plot for this atom, the energy plot will be like this. In this energy plot, as you can see, the S subcell is completely filled. This is the S subcell, this is completely filled, and the L cell is also completely filled with 2 electrons in the S subcell and 6 electrons in the P subcell, whereas the M cell is not completely filled, it is partially filled with 2 electrons in the S subcell and 2 electrons in the P subcell. So, out of 8 vacancies of electron, only 4 are filled and 4 are unfilled. Now, this is an isolated atom of any arbitrary atomic number 14. This is an isolated atom, and this is the electronic configuration and energy levels of these isolated electrons. And these energy levels are very much distinct, they are quantized, and this we concluded from the quantum mechanical theory of atom. That quantum mechanical law says the energy of electrons in a free and isolated atom cannot have arbitrary values, but only some definite or quantized values they can have. These are those definite and quantized values of those electrons. Now, let us consider there are two electrons. Let us bring two atoms, let us bring two atoms close together, two such isolated atoms close together as shown in this picture. If you are bringing two atoms close together, then what will happen? The 4 electrons of the outermost shell of this atom will interact with the 4 electrons of the outermost shell of this atom. And as a result of this interaction, the energy levels of these electrons, allowed energy levels of these electrons will be modified little bit. Some energy levels will go down, some energy levels may go up. So, as a result, the outermost valence electrons 3s2 and 3p2 of each atom will interact with each other to modify the energy levels, and there will be two closely spaced energy levels for 3s2 and two closely spaced energy level for 3p2, and the energy level diagram will look somewhat like this. Here you can see that 3s2 is having two closely spaced energy levels and 3p2 is also having two closely spaced energy levels. Instead of being very distinct energy levels, the energy levels has been modified and they are displaced little bit. Whereas, the energy levels of the inner electrons, they have not been modified to a large extent. There also some modification is there, but very small modification is there. You cannot observe those modifications. The energy levels of the inner electrons like 1s2, 2s2, 2p6, they will also get modified slightly, but they are not appreciable. Those modifications are not to a large extent, they are not appreciable. Only the modification of energy levels of the outermost electrons is appreciable. Now, further consider that 4 such atoms are together. Let us bring 4 such atoms together as shown in this figure. Now, what will happen? The outermost electrons of those 4 atoms will interact with each other, and hence there will be 4 closely spaced energy levels for 3s2 also and 4 closely spaced energy levels for 3p2, and the energy level diagram will be somewhat like this. Here you can see that again the energy levels of the inner electrons are not changing much, though they are changing, but the change is or that modification is not appreciable, whereas this energy levels of 3s2 and 3p2 has changed quite appreciably, and you are seeing 4 closely spaced energy levels for 3s2 and 3p2. So, what you concluded from here? Now, this shows that if an atom is isolated, then their energy levels of electrons are clearly distinct. They are separate from each other and they are very clearly distinct, quantized. However, when an atom or some atoms belongs to a crystal, then the energy levels are modified. The energy levels of at least outermost electrons are modified. Some energy levels will come down and some energy levels will come up, and they will make a band of energy. Some energy levels will be modified and they will make a band of energy. This modification is not appreciable obviously for the inner electrons, whereas this modification is appreciable for outermost electrons. Now, let us consider a crystal of silicon having n number of atoms. Let us consider a crystal of silicon having n number of atoms. Now, each atom is associated with a lattice site. When there is a crystal, an atom cannot sit at any place. There is a certain rule there is a certain place for an atom to sit at. Those places are called lattice points. Okay, those places are called lattice points, and an atom or a group of atom or a molecule has to sit or must have to sit on that lattice point. This is the rule. Now, each atom has sit on the lattice point, and the electronic configuration of silicon is same, because atomic number is 14, the same example we had taken. So, this electronic configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Now, for this silicon crystal having n number of atoms, now let us draw the energy levels versus interatomic separation. For example, suppose this crystal is made up by bringing all atoms close together slowly. That means, bring all atoms, all n number of atoms slowly close to each other and try to make them sit on the particular lattice point. Now, in that process, you are decreasing the distance between two atoms. That distance between two atoms is called interatomic separation. Now, when you are decreasing the interatomic separation, how the energy levels are getting modified, that is what we are going to see now. Now, let us draw a plot between the interatomic separation or interatomic spacing R and the energy levels for this crystal of silicon consisting of n number of atoms. Now, in this crystal, 2 electrons are there in the 1s2, 2 electrons are there in 1p, 2p2, and 6 electrons are there in 2p, 6 electrons. 2 electrons are there in 3s and 2 electrons are there in 3p. Now, since there are n number of atoms, the outermost energy levels, these 3s2 and 3p2, this 3s2 energy level and 3p energy level will be having 8n number of energy levels, right. Since there are n number of atoms, 2n number of energy levels will be there for 3s and 6n number of energy levels will be there for 3p, because s orbital can have 2 electrons, one for up spin, one for down spin. So, there are 2 available energy level for s, and similarly, since p subcell can have 6 electrons, 2 for px, 2 for py and 2 for pz, and hence p subcell can also have 6 energy levels. So, in a total, one atom of silicon can have 6 plus 2 8 energy levels in the outermost cell 3s and 3p. Hence, for n number of atoms, there will be 8 n number of cell energy levels for the outermost cells. For this outermost cell, this M cell, there will be 8 n number of energy levels. This inner atomic state, this inner or energy levels are called ion core state. Those are called core state. They are not going to get modified appreciably. That is why they are called core state, whereas these are called outermost state. Now, divide this entire range of interatomic spacing into 4 regions. Okay, into 4 regions. Suppose OA, this OA is the final interatomic distance of separation. The OA or some less than OA is final interatomic distance of separation. You cannot bring closer than that. And we are dividing the entire interatomic separation into 4 phases: OA, distance OA, distance OB, distance OC, and distance OD. And we will conclude our we will carry out our analysis based on these 4 distance of interatomic separation. Now, there are 6 cases can possible. Case 1, when the interatomic separation is greater than OA, R is greater than, very greater than OA. Suppose OA is the equilibrium separation, R is very greater than OA, that is R is suppose OD. If R is OD, that means when the interatomic separation is of each atom is equals to OD, then what is the situation, what is the scenario? That is one case. Second case, when R is in between OC and OD, this is OC and this distance is OD. When R is somewhere here, when the interatomic separation is somewhere here, then what is the situation? Then another scenario is R equal to exactly OC. At R, when R will be OC, interatomic separation is equal to OC, what will be the situation? What will be the situation when R is in between OB and OC? This is OB and this is OC. What will happen when R will be somewhere here, somewhere here? What will happen when R will be exactly OB? What will happen when R will be exactly equal to OB? And what will happen when R will be equal to OA? These are the 6 cases we are going to discuss when you are bringing silicon atoms close together to form the crystal. In the process of crystallization, these are the 6 situations we are going to discuss now. Now, when R equal to OD, you can see that when R equal to OD or greater than, very greater than OA, that means when the atoms are almost isolated, all atoms are almost isolated, what you can observe, you can see that all the energy levels of all atoms, all the energy levels of all atoms are clearly distinct. They are clearly distinct and they are exactly equal to each other. That means the energy level 3s energy level of first atom, second atom, third atom, fourth atom, all n number of atoms will be having same energy values, whereas these 3p energy levels of all atoms will be having same energy levels. When the atoms are isolated from each other, the interatomic separation distance is very much greater than the equilibrium value. That means OD or R equal to OD, which is very much greater than OA. So, the energy levels are very much distinct, they are clearly distinct. Now, if you are decreasing further the interatomic distance of separation, if you are decreasing the further the interatomic distance of separation, that means in this region you will see that there is a tendency of modification. There is a tendency, still there is no modification, but they are going to start modifying their energy levels. There is a tendency of modification of energy level. At exactly R equal to OC, at exactly R equals to OC, that means at exactly this line, at exactly this position, the energy levels start spreading. That means the energy levels start getting modified. That means some energy levels out of there are 8 n energy levels. In this M cell, there are 8 n energy levels. Some energy levels are getting reduced value and some energy levels are getting value little bit higher. That means they are getting modified and they started spreading at R equal to OC at this position. They will start spreading. Now, in this process of spreading, here in this area there will be 2 n energy levels, and in this band there will be 6 n energy levels. This spreading of energy levels is called formation of a band. Now, the energy levels are not discrete, the energy levels are now a band of energies. In this band there will be 2 n, because s orbital for n number of atoms will be having 2 n energy levels. So, in this band there will be 2 n energy levels, and in this band there will be 6 n energy levels. So, the 2 n energy levels will spread separately of 3s and 6 n energy levels of 3p will start spreading separately. Now, at a position OB less than R less than OC, that means at a position exactly R equal to OB at this position, at position exactly R equal to OB, all of these 8 n energy levels, will merge with each other. You can see from the figure, let me highlight that portion. You can see from the figure that all these energy levels are getting modified, are getting merged. All these energy levels, 8 n number of energy levels are merged together, okay, at R equal to OB. They started merging with each other. Now, when they merge with each other, out of 8 n energy levels, 4 n energy levels are filled, means 2 n energy levels of s orbital of each atom and 2 n energy levels of p orbital of each atoms are filled, and 4 n energy levels of this p orbital are empty, means 4 energy levels of p orbital of each of the n atoms are unfilled. That means, this 4 n energy levels of p orbital are vacant or empty, whereas the 4 n energy levels of this s and p orbital are filled. Now, all these 8 n energy levels are merged with each other, and out of those 8 n, 4 n energy levels are filled and 4 n energy levels are empty. Now, when you further decrease the distance, that means at a position r equal to OA, that means this line, at a position r equal to OA, which is the equilibrium distance, which is the final distance or interatomic lattice separation or lattice constant at r equal to OA, you will see that these merged energy levels again got separated. These merged energy levels again got separated, and now the separation has taken place in a different way. What is that way? Out of those 4 n energy levels, 8 n energy levels, 4 n energy levels will be filled energy levels will be separate from the other 4 n energy levels. Out of those 8 n energy levels, they will be divided into exactly half, 4 n in the down, 4 n in the down means having less energy, and rest of the 4 n energy levels having more energy. And these 4 n energy levels, these 4 n energy levels are completely filled with electrons, because you know that 4 n energy levels are filled with electron, and these 4 n energy levels are completely empty of electron. These 4 n energy levels are completely empty of electron. This will happen after this point. This will happen after this point of separation. So, at a equilibrium separation of OA, you will see that these merged 8 n energy levels again has been separated, and with 4 n energy levels going down, which are completely filled, and 4 n energy levels going up, which are completely empty at equilibrium separation. And the lower energy levels, which are completely filled with electrons, are called valence band. That is a band of energy, levels, and this lower band of energy levels, which are completely filled with electrons, are called valence band, and the higher energy levels, which are completely empty, which are not having at all electron, are called conduction band. And the distance of separation, that means the gap of energy between this valence band and conduction band, is called forbidden energy gap. The separation between the highest level of valence band, and lowest level of conduction band is called forbidden gap or energy gap, forbidden energy gap or band gap, they are called. Okay. So, this is the pictorial representation of the fact which will happen when you are bringing atoms close together to form the crystal. The mathematical description of all these things are there, mathematically also you can find out the energy levels, their distance of separation, sorry, their energy gap, energy separation, everything you can find out by using quantum mechanics. But those are not belonging to your syllabus. Whenever you will go to a higher study, you will study about those quantum mechanical models to calculate all these things. But for time being, for now, for this course, you just need to have a pictorial realization of what the things are happening when atoms are atoms are brought close together to form the crystal, and this is that thing happening. Now, let us have a recap of this. Now, when R equal to OD, when R was OD, I am just reading out the conclusion points. I am not going to everything has been discussed. Now, I am just reading out the conclusion points. Now, when R was equal to OD, which is very greater than the interatomic separation, that means at this line each n atom has its own energy levels, and the energy levels are identical, sharp and discrete and distinct. All energy levels are identical, sharp, discrete and distinct. So, the outer two subcell 3s and 3p of n cell or n equal to 3 cell of silicon atom contain 2 s electron and 2 p electron, 2 s electrons and 2 p electrons. So, in a total for n number of silicon atoms, there will be 2n electrons completely filling 2n possible s levels, all of which are at the same energy, So, these for n atoms, these 2s 3s level is completely filled with 2n number of electrons. Out of 6n possible p levels, only 2n are filled. Out of 6n possible p level, only 2n are filled with electron, and rest of the 4n of the energy levels are empty. This is the situation when R is equal to OD, which is very greater than the equilibrium distance of separation. Now, when OC is less than R less than OD, means at this position, in the middle, you will find that there is no visible splitting of energy levels, but there develops a tendency for splitting of energy levels. There is no visible splitting of energy levels, but there develop a tendency of splitting the energy levels at this point, in this region. And at the point when R equal to OC exactly, you will see that the interaction between outermost cell electrons, the interaction between the outermost cell electrons of neighboring silicon atoms becomes appreciable, and the splitting of energy levels commences. The splitting of energy levels starts at this point. Now, when in this region where OB is less than R less than OC, that means in this region, you will see that the energy corresponding to the S and P levels of each atom gets slightly changed. The energy levels get slightly changed. Corresponding to a single S level of an isolated atom, we get 2n levels. We get 2n levels here in this below band. We get 2n levels. Similarly, we will get 6n levels in the top band. So, the energy levels are now splitting, and this splitting of energy levels is happening for 2n energy levels for the below energy level, 3s energy level, and that is happening for 6n energy levels in the p subcell. Now, when R equal to OB, when at this point R equal to OB, what will happen? The energy gap disappears completely. The energy gap between 3s and 3p disappear completely, and all of the 8n levels are distributed continuously, and we can only say that 4n levels are filled and 4n levels are empty. Out of these 8n levels, 4n levels are filled and 4n levels are empty. At R equal to OA, at this equilibrium distance, again you find that the band of 4n filled energy levels, this is the band of 4n filled energy levels, this is the band of 4n filled energy levels. the band of foreign field energy levels is separated from the band of foreign unfilled energy levels by an energy gap called forbidden gap or energy gap or band gap. Okay. So, this was the recap of the thing what I discussed using that figure. Now, the lower completely filled band, this lower completely filled band is called valence band with all electrons present there, and the upper completely unfilled band is called conduction band. This is called conduction band of energy. Now, let us classify the solids into metals, semiconductors and insulators, and this classification is for solids only, not for liquids or gases, and this classification can be carried out in two ways: on the basis of electrical conductivity or resistivity, on the basis of energy band gap. The classification of solids into metals, semiconductors and insulators can be carried out in two ways. First, on the basis of electrical conductivity or resistivity, second on the basis of energy band gap. Now, let us classify the solids on the basis of conductivity, electrical conductivity or resistivity. According to this, on this basis, on the basis of conductivity and resistivity, metals are those who have very high conductivity and low resistivity. Metals are those who have very high electrical conductivity and low resistivity. Now, since conductivity and resistivity are inversely proportional to each other, they are reciprocal of each other, this is very obvious that if the conductivity is high, then resistivity will be low, and if the resistivity will be high, the conductivity will be low. So, this is very much obvious. Now, let us see the numbers. Okay. Now, for a metal, the resistivity falls in the order of 10 to the power minus 2 to 10 to the power minus 8 ohm into meter. The resistivity of metals falls in the range of 10 to the power minus 2 to 10 to the power minus 8 ohm into meter, whereas the conductivity will fall in the range of 10 to the power 2 to 10 to the power 8 Siemens per meter. Now, you can see clearly, since resistivity and conductivity are reciprocal of each other, the numbers are also reciprocal of each other. That means, if the resistivity is lying in the range of 10 to the power minus 2 to 10 to the power minus 8, the conductivity is lying in the range of 10 to the power 2 to 10 to the power 8, which is nothing but reciprocal of these numbers, reciprocal of this range exactly. So, you can specify either resistivity or conductivity to classify whether a solid is metals or not. Now, the examples of metals are aluminum, copper, some metals are the aluminum, coppers, bronze, like some metals are there. Those are very good conductors. Now, come to insulators. Insulators are those materials or those solids which have very low conductivity and high resistivity. Just opposite to metals, insulators are those solids which is very low conductivity and high resistivity. In terms of numbers, the resistivity of insulators fall in the range of 10 to the power 11 to 10 to the power 19 ohm into meter, whereas the conductivity falls in the range of 10 to the power minus 11 to 10 to the power minus 19 Siemens per meter. So, these are the numbers, and the examples of insulators are like wood. Wood is a good example of insulator that do not pass electricity through it. They do not conduct electricity through it. That is why its resistance is very high. Some ceramics are also good resistance of good insulators of electrical. I mean, good. Some ceramics are also good insulators. After that, The semiconductors are those which have conductivity which lies in between the conductivities of metals and insulators, and the semiconductors are having resistivity which lies in between the resistivities of metals and semiconductor. Hence, semiconductors are solids, those solids which have conductivity and resistivity which lies in between metals and insulators, the conductivity and resistivity of metals and insulators. And obviously, the numbers will lie in between. The resistivity is of the order of 10 to the minus 5 to 10 to the 6 ohm into meter, and the conductivity will lie in the order of 10 to the 5 to 10 to the minus 6 Siemens per meter. And the good example are silicon, germanium, these are semiconductors, naturally occurring semiconductors. These materials these solids are called semiconductors, whose conductivity and resistivity falls in between the conductivity and resistivity of metals and insulators. Now, on the basis of band gap, we can identify metals in two ways, in two scenarios. In one scenario, the conduction band is partially filled. There is a gap between valence band and conduction band, and the conduction band is partially filled. And another scenario is the case. So, in this first scenario, the first possible energy band diagram of a metal is that in which the conduction band is partially filled. Though there is a gap between valence band and conduction band, the conduction band is partially filled. This is the first scenario. The conduction band is partially filled. In this case, if there will be little energy, supplied to these electrons will go to higher energy levels of the conduction band, and they will start conducting. With a little extra energy. Now, another case is a case in which the valence band and conduction band are overlapped with each other. This is the case where the valence band and conduction band are overlapped with each other. That means, there is no energy gap between the valence band and conduction band. That means, there is no existence of forbidden band or forbidden energy gap in case of metals in this scenario. In this scenario, if they are overlapped, then obviously these electrons are responsible for conduction. That means, they require very minimum energy. Since the conduction band is overlapping with the valence band, in this case also they require very minimum energy to go up to the conduction band and start the process of conduction. Okay. Now, in the first case, the maximum energy level, the electrons can possess at absolute 0 degree Kelvin are called Fermi energy level. The energy level, the maximum energy level, the electrons can exist or can possess when the metal is in absolute 0 degree Kelvin temperature. That energy level is called Fermi energy level, and at absolute 0 degree temperature, metals also behave as insulator. Please remember it, at absolute 0 degree Kelvin temperature, metals also behave as insulator, and the maximum energy possessed by these electrons are called Fermi energy level. And to have conduction, to conduct electricity, the electrons has to go out of this Fermi energy level. That means, if you will supply some energy, then these electrons will gain some energy and they will get excited out of this Fermi energy level and they will start conduction. Okay. If the electrons get enough energy to go beyond this Fermi energy level, then conduction occurs. After crossing the Fermi energy levels, even with a very small supply of potential, these electrons start conducting, and that in that case it's called a metal. Now, I mean now in case of semiconductor, the gap between valence band and conduction band is existing, and that gap, value of that energy gap is around 1 electron volt, is around 1 electron volt. If the value of the energy band gap is around 1 electron volt, then that solid is called a semiconductor. For example, in case of silicon, the energy gap is around 1.1 electron volt, and in case of germanium, the energy gap is around 0.7 electron volt, and which both are nearby to 1 electron volt. So, the solids in which the forbidden energy gap or the band gap between the valence band and conduction band is around 1 electron volt, those solids are called semiconductors. Those solids are called semiconductors. In this case also, at absolute 0 degree Kelvin, no electron has enough energy to jump from valence band to conduction band. At absolute 0 energy, no electron has enough energy to go from valence band to conduction band. Hence, the crystal will be called as an insulator. At absolute 0 degree Kelvin, the crystal will be called as an insulator. But when a slight temperature will be supplied, when the slight heat energy will be supplied, that means at room temperature, even when you are bringing that crystal to a room temperature, some valence electrons get more energy than the energy gap. Some valence electrons, some of these electrons will get more energy, and they will be excited to the conduction band by leaving a deficiency of electron in the valence band. Okay. So, those electrons which are getting excited to conduction band then will take part in the process of conduction. Those electrons will take part in the process of conduction. So, at absolute 0 degree Kelvin, the the semiconductor will also behave as an insulator, but when the temperature rises, when you are supplying slightly heat energy, the electrons will be excited to the conduction band, and they will start taking part in the process of conduction. When one electron will be excited to the conduction band due to the supply of heat energy, when electrons will be excited to the conduction band, some deficiency of electrons will be there in the valence band. Some deficiency of electrons will be there in the valence band, and those deficiency of electrons are called as holes. Those deficiency of electrons are called as holes. Holes is not an entity which has physical existence or physical space. Hole do not occupy a physical space. It is just a mathematical concept which is adopted by us for our convenience. For the simplicity of explanation, we have adopted the nomenclature of holes. Otherwise, holes do not exist in reality. Holes do not occupy any physical space. We will discuss in detail about the holes in the next video lecture. For time being, holes is the deficiency of electron. When an electron jumped from or excited from valence band to the conduction band, a hole will be created in the valence band, and the number of electrons and number of holes created due to the supply of heat can be found out using this relation. The relation is number of electrons n and number of holes or number of holes p is equal to e to the power minus E g divided by k b t, where this E g is nothing but this band gap energy, this E g is nothing but this band gap energy, this k b is called Boltzmann constant, and this T is called temperature, the temperature at which you are finding out the number. Now, from this equation, it is very much clear that the number of electrons created in a semiconductor will be exactly equal to number of holes created in that semiconductor. That means, by the process of thermal agitation, by giving thermal energy, the number of electrons you are able to create in the conduction band will be exactly equal to the number of holes generated in the valence band, the number of difference of electrons generated in the valence band, and both the numbers are equal, and hence this equation is read like this: n, which is number of electron, p, which is number of holes, is equal, and they are equal to a number which is given by the formula e to the power minus Eg divided by kBt. Okay. Now, since in case of a semiconductor Eg is very small, with very little temperature, you can get very high number of electrons for the process of conduction. We will do some numerical based on this formula. Now, such unfilled regions are called. Okay. Now, for our convenience, we have taken the Now, as an let me recap whatever I told. As an electron leaves the valence band, it leaves an energy level in the band as unfilled. Such unfilled regions are termed as holes in the valence band. They are taken as positive charge carriers mathematically for our convenience. They do not have any physical space. In reality, they do not occupy any physical space. Any movement in this valence band is referred as positive holes moving from one position to another. If there is any movement in these holes, then it is referred as the holes are moving from one position to another. Those things we will be discussing in detail in the next video lecture. Now, what is an insulator based on this band gap energy? Insulator are something which have energy band gap which is more than 6 electron volt. If a solid is having forbidden energy gap more than 6 electron volt, energy difference more than 6 electron volt, then those solids are called as insulator. Okay. If the energy gap is very large, the solids are called insulators. Now, it is not that easy to take some electrons from valence band to conduction band to have the conduction process possible in case of insulator by giving some thermal energy. In case of insulator, by giving some thermal energy, it is very difficult to take electrons or excite electrons from valence band to conduction band and thereby to take part in the process of conduction. Okay. That is why they are called as insulator. The example of insulator are diamond, whose band gap energy is around 7 electron volts. Okay. So, insulators are those solids which have band gap energy greater than equal to around 6 electron volt, those are called insulators. Okay. Now, let us have a recap on the concept of electrons and holes. As you are going to discuss in detail about semiconductors. Okay. Now, this was all about the classification of solids in as conductor, insulator and semiconductor based on both band theory of solid as well as this conductivity and resistivity. Now, from now onward, we are not going to discuss in detail about the conductor and insulator, and since it is semiconductor electronics, we are going to discuss in detail about semiconductors in the coming video lectures. Now, in case of for that it is wise to have a recap of the concept of electrons and holes. Now, in case of a semiconductor, on receiving an additional energy, some of the electrons from a covalent bond breaks and is free to move in the crystal lattice. Okay. Those are called free electrons. Okay. On receiving an additional energy, some of the electrons from a covalent bond breaks and free to move in the crystal lattice. While coming out of the covalent bond, it leaves behind a vacancy named as hole. While coming out of the covalent bond, it leaves behind a vacancy called as hole. An electron from the neighboring atom can break away and can come to the place of the missing electron or hole, completing the covalent bond and creating a hole at another place. Thank you.